Thanks everyone for joining. This is Trillium Flow Technologies webinar, Vertical Pumps for Water Markets, Key Selection and Design Configurations. Just before we start, a couple of housekeeping items. At any time during the webinar, please feel free to ask questions. There is a question and answer chat box at the bottom of the Zoom window. Just click on it and type your question in. We will leave time at the end to try and answer those questions, and we will try to answer as many as we can within the time allowed. So please make use of that at any time. Also, this webinar is recorded and it will be available on the Trillium Flow Technologies YouTube website 2 or 3 days after the conclusion of this webinar. So with that, let's get started. Next slide. So we'll go into the overview, just to talk about the presenters. Myself, I'm Simon Bradshaw. I'm not going to read all of what's on the slide there because you guys can read faster than I can. Suffice it to say, I've been doing pumps and valves a really long time with a bunch of different companies. I'm now with Trillium. I do it because it's frankly a lot of fun and I keep learning new things out pretty much every day. My co-presenters, who are significantly smarter than me and will do all the heavy lifting on this presentation. First of all, we have Matteo Tiselli, who is based out of our La Spezia, Italy site, and he's the head of the Beshaft Pumps department. He's been with Trillium almost 21 years. He has very extensive experience in both vertical and horizontal pump designs, and he holds a master's degree in mechanical engineering from the University of Pisa. The co-presenter is Steve Kazanza. He has 12 years of experience in vertical pumps out of our site in Fresno, California, and he is an advanced product engineer. He holds a master's science degree from the University of California in Los Angeles. Okay, so let's talk about a little bit about Trillium Flow Technologies itself. We manufacture mission-critical equipment such as pumps and valves, and we also provide aftermarket parts and service to the global power generation industry, wastewater, oil and gas, and other aftermarket oriented process industries. So in blue, you can see our pump brands, and in green are the valve brands. And in particular, on the pump brands, we've kind of called or highlighted the three pump brands that we're really going to be talking about in this webinar. So we'll mention those in a moment. We have a total of 17 long-standing trusted brands dating back 165 years that are globally recognized. We also have 11 manufacturing facilities and 4 service centers located throughout the US, UK, France, Italy, Netherlands, South Korea, China, India, and around 2,000 employees globally. If we take a look at the brands that we represent, on the valve side, we have Atwood and Morrow, isolation and check valves, Autotorque actuators, Batley butterfly valves, Blake-Burr control and choke valves, Hopkinson parallel slide gate and globe valves, Saracen and Sabine safety valves, as well as Tricentric triple offset butterfly valves and Red Point ball valves, all leading names in the industry. On the pump brand side, the specific ones we'll be covering today and that are highlighted include Flowway pumps, Gabi and Etta pumps, and Thermomechanica pumps. So with that, we'll go just also mention on the right-hand side, it just shows our global footprint. In other words, we have 21 facilities around the world, plus a network of third-party sales and authorized service centers. That enables us to be where our customers are. With that, we'll go to the next slide. This is just a bit of a timeline showing the evolution of Trillium. We have a long heritage. It spans about 190 years. The 3 pump brands that we're being discussed today, which are, as I mentioned, Flowway, Gabi, Etta, and Thermomechanica, were respectively founded in 1934, 1912, and 1897. So they represent a wealth of capability and experience, and enables us to offer highly engineered solutions to our customers. Throughout this history, we have continued to improve our products and to add new products and services to our portfolio in order to serve our customers' processes more efficiently and more productively, and ideally lead to your success. Next slide. This just shows the overview of all of the pump designations that we offer. We're obviously going to talk about the verticals, which are in light blue, specifically today. But the point here is with this slide is that we do many others, types of pumps, pretty much any kind of pump you want. And on the right-hand side, it just mentions the industries that we serve. And with that, I'm kind of done. We'll hand over to my colleague, Steve Casanza, who will take it from here and outline the agenda of the webinar. Thanks, Steve.
Okay, well, thank you, Simon, and welcome everyone. So we'll start out with an overview of the agenda for today's webinar. First, we'll start with a vertical pump overview, where we'll answer the questions, number one, why use a vertical pump? And secondly, what different types of vertical pump are there and why do they all exist? Then we'll move on to key selection considerations, where we'll give an overview of some of the important information needed in order to make those selections. After that, we'll talk about recommendations for selection and specification. And then we'll get into some custom design options, where we'll give an introduction to some special features and designs for challenging services. Next, we'll move into some case studies, where we'll present a few examples of pumps in the field and the applications that they're being used on. And then finally, we'll have a summary segment, which includes a recap of the information covered, and then also some time for questions and answers. And let's see here. I'm sorry, I forgot to remember to flip the slide here. So to begin with our overview of vertical pumps, so we'll first explore the question of why do we want to use a vertical pump? One factor to consider is NPSH, which is net positive suction head. And this is a way of defining suction pressure relative to the vapor pressure of the pumped fluid. When NPSH is adequate, damaging effects of cavitation are avoided. So where the vertically suspended pump comes in is that it can be placed in a sump or barrel, thereby providing additional NPSH margin. And sometimes it's the only option when suction pressures are insufficient. Another factor that can favor the selection of a vertical pump is cost. The vertically suspended pump may be an economical option in certain applications. One example is a booster pump. Often it is lower cost to have a vertical booster standalone unit than to increase the suction pressure in the upstream system. Another advantageous aspect of a vertical pump is its relatively small footprint. So for example, you could have a very large pump with many stages that can take up a relatively small amount of floor space as compared to a comparable horizontal unit, provided that the below grade geometry can be accommodated. Now, having considered these things, we could also ask the question, why would you not use a vertical pump? And two key points are, firstly, ultra high pressure applications, which are oftentimes better served with a horizontal design. And the other reason is foundation restrictions, where it's not feasible to either install a suction can below grade or construct a sump type intake for the pump on site. So on this next slide, we have a matrix outlining the different vertical pump types for water applications. As you can see on this slide, there are many different types of vertical pumps, and each can be uniquely configured to meet the needs of each application and customer requirement. In the leftmost column are listed the water applications that are served by vertical pumps. These include seawater desalination, well pumps, water transportation and distribution, flood control, irrigation and land reclamation, as well as water treatment. And starting now in the first two columns, we have our first two variants, which are the VS1 and VS2 pumps. And as you can see from our table, these are versatile pump types that work in many applications. These are single casing designs with the intake of at the bottom of the pump, and they're therefore suitable for open sump, well, or raw water intakes such as canals, and reservoirs and other open bodies of water. The distinction between the VS1 and VS2 is in the casing design. The first being a diffuser type, which is sometimes referred to as a bowl type diffuser, and the other being a volute. The bowl type diffuser of the VS1 is a compact design that is well suited to reaching higher pressures by adding stages to the pump, while the volute of the VS2 is generally for higher flow, lower head applications, and it's amenable to double suction designs that offer low thrust. Now, moving on to the next pump variant, we have the VS3, and this is a pump that is similar to the VS1, and it's distinguished by a flow path that runs straight through the impeller without turning. These are sometimes referred to as propeller pumps, and this category of pumps is really more of a hydraulic distinction than difference in construction. These pumps are well suited to delivering high flow capacity at low head. Our next pump type is the VS4 pumps, and these have a volute style diffuser similar to the VS2. But the difference here is that the high pressure discharge exits in a separate pipe that is brought to the surface. And this discharge pipe can be seen here on the left side of our illustration as a separate line running up to the surface, parallel to the main column pipe. This design allows for a simpler sealing arrangement where the shaft exits the casing near the top of the pump, as it doesn't see the pressurized fluid. And it's also beneficial when pumping fluids with high abrasives, as the shaft bearings are bypassed. The next pump type in the table is the VS0, or submersible type, which is characterized by having a submerged motor that resides at the very bottom of the pump. This design is well suited for deep well applications. It eliminates the need for a seal where the shaft would otherwise exit the pressurized casing, as well as the line shaft and bearings that would otherwise be present between the impellers and the above grade motor. And this can represent substantial savings in the case of a deep well pump, which can be hundreds of feet long. And moving on to the next two columns, we have the VS6 and VS7 pumps, which are the double casing variants. And these are essentially VS1 or VS2 pumps that are enclosed in a suction can, which is also in the industry referred to as a barrel. These pumps are designed to connect to water supplied via piping, as opposed to the open sources seen with the VS1 and VS2. And these are often used as booster pumps. Finally, there is a special design category, which includes Trillium's concrete volute designs, which you'll hear more about later in the presentation. On this slide, we're going to introduce some of the major components and assemblies of a vertical pump. So starting with the driver at the top, the driver is typically an electric motor, but it can also be a right-angled gear drive connected to a diesel engine, or even in some cases, a steam turbine. There are two main electric motor types, and these are the hollow shaft and solid shaft. The main difference being that the former permits adjustment of the shaft running position, or the rotor running position at the top of the motor, and while in the latter it's performed via a separate coupling located below the motor and within the discharge head. Now going to the next assembly below the driver, we have the discharge head, which is where the fluid is turned and exits the pump. And this can either be cast or fabricated, which we'll get into a bit more later in the presentation. Also contained within this assembly is some means of sealing at the point where the shaft exits the pressurized casing. And this is typically either a packing box or a mechanical seal. For mechanical seals, there is also usually a rigid spacer coupling located in the upper area of the discharge head that permits access to the seal for maintenance without removing the motor. And this also provides the shaft adjustment mentioned previously with the solid shaft motors. The column assembly is essentially a length of piping that also contains the line shafting and bearings that drive the pump impellers, and it conveys the fluid from the bowl assembly below up to the discharge head. Standardized column designs can be configured to the length required by the customer, which ranges anywhere from around 5 feet up to several hundred feet in length in the case of a deep well pump. The column pipe can be configured as threaded or flanged as required for the project. The bowl assembly, which is down at the bottom, contains the hydraulic pumping components, where the work is done on the fluid. And these include the impellers, the bowls or diffusers, as well as the bearings and shafting. All of these components have precision machined registers to ensure proper shaft alignment when assembled. So this concludes the overview of vertical pumps. And now we're going to move on to discussing some of the key considerations when selecting vertical pumps. The first consideration for pump selection is the availability laterally and vertically of space, the footprint that's available, as well as the location and type of the pump suction and the discharge. This determines the overall type and configuration of the pump, from among the variants we've just seen. And also it determines the overall length of the pump, which is sometimes referred to as the setting. The next key consideration for pump selection is the flow and the pressure or head that's required. These are fundamental pieces of information used in the pump selection. From these, we can determine the pump hydraulic model, the rated shaft speed, the staging needed, as well as the impeller diameter. The next consideration is duty cycle, which determines the emphasis that's going to be placed on efficiency and any measures that are taken to maximize it. For example, in a fire pump that operates intermittently, efficiency is usually not a critical aspect of performance. Conversely, for a pump in a municipal water facility running continuously around the clock, obviously efficiency then becomes critical in terms of its impact on operating costs. This slide shows performance curves for some VS6 pumps that were supplied for a municipal water application using recycled water in a residential irrigation system. And it illustrates a number of additional considerations in pump selection. Now, the first of these considerations is whether the pump will be operated in parallel or in series in the case of multiple pumps. And also, are there any scenarios where there are different numbers of pumps operating? In this case, the selection was evaluated for scenarios with 2 or 3 pumps operating in parallel, as well as a single pump operating alone. This is reflected in the plot shown, where 3 sets of performance curves can be seen, representing 1, 2, and then 3 pumps in operation as you look at the groups starting from left to right. The set of curves that's slightly lower on the plot that run laterally and slope downward from left to right are the pump's pressure or head curves. And then the upper set of curves that are dome-shaped are the pump's efficiency curves. And so, as you can see from the plot, as we increase the number of pumps operating in parallel, it becomes a flow capacity multiplier. So the pumps, stretch out increasingly to the right into increasing flows as the number of pumps is increased. So the next consideration seen in this example is the best efficiency flow of the pump. And in particular, how does it compare to the required conditions of operation? And so this can be seen in the curves on the plot. If we look at the rightmost point, which is represented by one of the blue triangles, the rightmost one here at 1,600 gallons per minute. And in this case, we could see that if we compare it to the efficiency curves for 3 pumps operating up above, it's very well matched to the point where pump efficiency is maximized. And so this is a very desirable outcome when selecting a pump for high efficiency. And then finally, we have the third consideration illustrated here, and that is the speed range of the pump, whether it's being operated at constant speed or operated on a VFD. So in this case, the requirements of the job were such that a VFD was needed, where the customer wanted to achieve a number of operating conditions along their system curve, which is plotted here with the red curve. And some of the conditions here for 3 pumps operating can be seen with these additional points in blue that are plotted. And so that was part of the evaluation of this pump selection, was just a verification for each of these multiple pump scenarios that the various operating conditions could be achieved with a reasonable speed reduction. And you can see the multiple speed curves are represented here with the multiple sets of dotted lines. So we have 4 speeds for each of the 3 cases of the different number of pumps operating. And just as a side note, an additional part of the evaluation, typically when we have a VFD pump like this, is that at a minimum, there's an engineering evaluation of structural vibration to ensure that no damaging vibration occurs within the operating range. The larger the speed range, the more challenging this can be. So now we'll move on to another example that illustrates a few more considerations for pump selection. In this example, we have a set of 9 VS1 well pumps and a potable water application. One aspect of this job was that a minimum efficiency was required by the customer. And so in this case, a couple of things were done to achieve the specified performance. Number one, a hydraulic selection was made where the best efficiency flows of the pumps were well matched to the operating conditions, similar to what we saw in the prior example where we looked at the best efficiency flow of the pump. But in addition, on this case, to meet the specified efficiency, we had to also include some efficiency enhancing and features within the pump construction. And these included things like extrude honed impellers and enamel lined bowls, both of these serving to create a smoother, higher surface smoothness within the hydraulic passages and less friction internally. And then additionally, we provided tapered column transition pieces, which creates a smoother flow transition where the fluid exits the bowl. And then also, as you can see in the picture here, we had a mitered discharge elbow, which is part of the discharge head that also provides relatively smooth turning of the fluid as it passes through the discharge head. So all of these things serve to reduce the losses, the hydraulic losses, specifically within the pump. The next consideration for selection is the pumped fluid itself, as well as the application. In general, a significant aspect when considering the pump fluid is the presence of abrasives, solids, or corrosive elements that will affect the material selection and construction of the pump. In general, Trillium has a range of options for different applications to address various needs. For this particular case, where the requirement was pumping potable water, Trillium supplied an NSF 61 certified pump. And when this type of product is supplied, a certain menu of materials, coatings, and components is driven, based on the requirements, for clean drinking water applications. And moving on to the third point, another consideration is whether the construction at the pump facility will be newly built or whether existing construction will be reused, meaning such things as equipment pads, suction cans, and/or piping. This determines the degree of customization that's involved in the design of the pump, in particular the discharge head and the sole plate to which it mounts in the case of a single casing type pump. A cast head with a standardized geometry is usually not an option in these cases. In the case of the VS1 pump in this example, existing construction was utilized, including the pump pads and even the anchor bolts that were already cast into the concrete. In order to accommodate this requirement, Trillium supplied tailored sole plates in 6 different configurations. So that concludes this discussion of key considerations. We're going to move on to talking about recommendations for specification and pump selection. The first recommendation for pump specification is that consideration is given to the potential trade-offs between the initial cost and higher efficiency. If we reference the pie chart to the right, it really tells the story here where energy consumption and pump maintenance together comprise 65% of the total cost, while the initial pump equipment purchase amounts to 5%. So the takeaway from this is that to strictly focus on the initial purchase cost can wind up being actually more costly over the long run if these trade-offs aren't evaluated. The second recommendation, or really set of recommendations, has to do with making sure that key pump design characteristics are suitably defined. The first of these relates to secondary flow points, and the recommendation is that larger tolerance bands are considered for these as compared to the primary design condition in accordance with recommendations in the Hydraulic Institute standards. And this is driven by a recognition that these secondary points are subject to effectively additional tolerance stack up and uncertainty as compared to the primary operating condition. This is because the primary operating design point is directly targeted by selecting an appropriate impeller diameter, and so it could be more readily controlled. The next item, which is essentially clearly defining the MPSH that's available, helps to ensure the correct pump selection with respect to the suction conditions. And this includes considering a possible low MPSH first stage, particularly in the case of barrel pumps, or maybe lengthening the pump to achieve increased submergence. The next recommendation relates to dynamics, and that is to avoid specifying a minimum natural frequency that's above the operating speed range for a vertical pump. And this is because vertical pumps are long, flexible machines, sometimes with very massive motors. And because of these characteristics, they often have natural frequencies that are below their operating speed range. Proper engineering of the pump can ensure that damaging vibration is avoided, even with natural frequencies below their operating speed range. The last item regarding materials for NSF 61 pumps is to encourage flexibility in the specification, because in these cases, the manufacturer is selecting from a fixed menu of materials, coatings, and components that have already been validated via a program of testing conducted as a part of the certification. And one final recommendation on point number 3 is to work with pump vendors offering a comprehensive range of pumps and that do not limit the offering based on a narrow portfolio. And that concludes the recommendations. And now we'll move on to a discussion of custom design options and hydraulic configurations. And for that, I'm going to hand off the presentation to my colleague, Matteo Toselli.
And just to remind everybody, please, if you have a question, please put it in the Q&A chat box at the bottom, and we'll try and answer it at the end. Thanks.
Thank you, Steve and Simon, and welcome to everyone. Now we are going to speak about some custom design options and hydraulic configuration of vertical pumps. And first of all, some details on discharge heads, which are the connection pieces to the plant piping. These components can be cast or fabricated, bought for bigger sizes, or especially for bigger sizes, fabricated, of course. In that case, we are able to customize the heads according to the customer requirements. I'm referring to the discharge nozzle diameter and position to meet existing piping dimension, overall dimension limitation, of course, as well as high internal pressure requirements. And also we can customize a type of stuffing box for to meet the mechanical seal or packings, and so on. Standard material for cast heads is cast iron, but for special application like warm sea water, for example, special alloys can be used, like aluminum bronze. But the biggest flexibility can be obtained using fabricated components. That may be done with corrosion-resistant materials like duplex or super duplex stainless steel, as well as in carbon steel with internal overlay of non-corrosive materials like stainless steel, duplex, super duplex. For drinking water application, for example, for municipalities, we can comply to NSF 61 or other regulatory standards around the world using materials with low lead percentage and making 30-part tests and certification as needed. In the pictures on the right, you can see some different discharge head option executions. On the left, an example of a special head designed to allow a right-angle gearbox, often coupled with a cardan joint to turbines or to diesel motor, both used as the drivers. On the right, another special execution where the customer needs the discharge nozzle to be below the foundation. Next slide, please. Okay, let's speak now about some improvements that Trillium can do to reduce operating cost of the vertical pumps. Of course, it means maximizing efficiency. Each hydraulic geometry, the assembly of the impeller and bowl or impeller and volute, is optimized for high efficiency using CFD software, and then are tested to validate all the performances. The picture on the top right is just an example of an impeller bowl assembly analyzed with the CFD software, and in which we have shown the fluid streamline inside. All details of other components are optimized, not only the hydraulic geometry, in order to minimize the internal losses, like the geometry of the transition pieces over the pump bowl, like in the picture on the bottom left, or the elbow, the shape of the elbow of discharge head. But theoretic efficiency cannot be achieved without higher quality castings and surface finishing. For that reason, Trillium pays always attention on tolerances of the hydraulic parts, especially for high energy pumps, and applies coatings, glass or epoxy, polishing or extrude holding to get the best smoothness of the hydraulic surfaces. Next slide, please. One technology that Trillium can apply to get high efficiency and flexibility is the impeller with adjustable blades. This kind of impeller has optimized performance across different rated flow. By adjusting the angle of the blades, we can ensure that the pump operates at peak efficiency of best MPSH requested, regardless of the flow rate. In the picture, we can see an example of pump curves changing with the angle of the blades. This adaptability not only enhances performance, but also extends the life of the pump by reducing the risk of cavitation and wear. All these impellers are semi-open mixed flow type with medium-high specific speed and spherical hub. It means that single stage, it can be applied only to single stage pumps suitable for a wide range of application with high flow rates and low head. In order to allow the blades to rotate, it's necessary to have a spherical hub design like that shown in the picture on the top and the center of this slide. There are too many types of adjustable blades, the impeller, fixed angle blades and adjustable angle blades during operation. Fixed angle blades can be adjusted when the pump is not running, allowing the changes in the flow rate for future requirements. And this feature is particularly useful in case the pump will run at constant flow rate for a long time, and for adapting to changing operational condition without needing to replace the entire impeller. It can be done several times. In this way, the customer can always run the pump near the best efficiency point. On the other hand, adjustable angle blades during operation offer the ultimate in flexibility. In fact, these blades can be adjusted in real time while the pump is running, enabling immediate performance changes in response to various to varying operational demands. This capability ensures that the pump can maintain optimal performances and efficiency under fluctuating conditions, providing significant operational advantages. Next slide, please. For the previous type of pump, as well as the other vertical turbine pumps, the flow arriving at the suction bell is a fundamental aspect of the correct behavior of the pump. This is quite critical in pump installation on seawater intakes or when a Kaplan duct, a suction duct is used. Trillium has a wide range of experience in this type of installations, where a CFD or physical scale model test shall be made to identify hydraulic phenomena that can affect the performance of the pump, like vortices or suction press wheel and so on. Also, some improvements on the original water intake design are often suggested to the client in order to decrease, for example, the submergence of the pump or the distance from the bottom. And Trillium has the experience to design these special features like curtain wall, buffer cylinders, both preventing the air entering vortices from the water surface, or splitters to avoid the flow separation of vortices that can occur in the corner areas, like that is shown in the central picture and catched by using CFD software. In the two pictures on the right, the comparison of a vortex formation found both in model test and in CFD results shows a very good matching. In the left, you can see an example of a CFD obtained for a water intake with multiple pumps in operation. One of these pumps is in standby, and one of the three suction ducts is closed. This is just an example and one of the possible operative condition of a water intake. You can understand that the construction of a physical model and the number of tests you have to do for all the operative condition of the plant requires always long time and high cost. So the analysis with CFD software is a valid alternative that gives to the customer the opportunity to save money and time and to start the civil works sooner. The CFD study of the water intake and coupled suction can be performed directly by Trillium R&D department, providing optimization and time advantage for the customer. Next slide, please. An example of a suction data can be analyzed using CFD software and can be found in the image on the center of this slide, where there is an example of a concrete volute pump. This kind of pump, for this kind of pump, all the static hydraulic components, the volute and the suction duct, are made in concrete, and so completely integrated in civil construction. Therefore, the pump is completely customized for the application and for the needs of the customer. These pumps are always pull-out type. Then only the rotor and the cover must be lifted and dismantled for maintenance. In the picture on the right, you can clearly see how this pump is made. It is composed by an upper part generally installed in an upper floor, and a lower part, which is the one pull-out, with guide bearings into halves that are used for easy maintenance. Also, we use a special construction that allows seals to be removed without emptying the suction duct and dismantling the pump. As the volute and suction duct are in concrete, and because these pumps are often huge, then a skilled model pump must be realized and tested according to Hydraulic Institute standards. This kind of pump assures, especially for big size, several advantages. The reduction of the installation cost, for sure, minimal and easy maintenance, and corrosion and erosion resistance, and so the increase of the lifetime of the pump itself. Next slide, please. Vertical suspended pumps can be designed and supplied with special option to meet several requirements for the customer. The pull-out option used as a standard for a concrete volume pumps, as said before, is an option for all the single-stage diffuser pumps with high specific speed. With this solution, the inner part, which is composed by impeller, shaft, wear parts, guide bearing, and so on, is entirely removable from the outer part. The big advantage for the client is that after the installation at site, the outer part, that is the one with the biggest weight, remains installed and only the inner is moved. We will see an example in the following slide, while a sectional drawing of the pull-out pump is shown in the picture on the right. Another useful special option is the shaft protection sleeve, as shown in the upper picture. The sleeve protects the line shaft from dirty fluids, and the advantage for the customer is the possibility to pump non-filtered fluids, so avoiding big and very expensive strainer installed in the suction area. The guide bearings are in fact lubricating using a small amount of clean fluid, usually taken directly from the pump discharge and filtered with a small basket strainer. This is a very cheap solution for a big advantage. Other special components can be easily designed to meet all the customer requirements, like sole plates of every shape and dimension or anti-vortex devices to be installed both in the plant or directly on the suction filter, as shown in the picture. Next slide, please. Now I'm showing you some installation of pumps designed and installed for water application. The first one in this picture shows some flowway vertical turbine pumps for fresh water service at water utility plants. That's a high efficiency pump with a motor power almost 2 megawatts. The project was won based on offering industry leading efficiencies. These were achieved through CFD modeling and design combined with close manufacture tolerances and internal coating, as already explained. This is only an example of optimized design, but Trillium has the experience and capability to use existing hydraulics and design new hydraulics for almost every vertical application. Next slide, please. That's an example of in which the customer required a pull-out solution for a vertical turbine pumps in board. In the right picture, we can see the removable inner part lifted by crane. It is composed by an impeller, shaft bearings, and the upper part of the discharge head. It is a seawater pump at the Alhyd desalination plant with more than 34,000 cubic meters per hour, 33 meters of head, and a motor of more than 4 megawatts. Next slide, please. That's one example of a huge impeller, almost 3-meter diameter. As I said, this is a concrete volute pump. It was supplied for the biggest pumping station in India, Sardar Sarovar Dam, for land reclamation and irrigation. The flow rate is 72,000 cubic meters per hour, 4 megawatt erratic motor, but only 60 meters of head. Next slide, and let's switch to the quick recap of this webinar. We have spoken about the needs for vertical pumps, and they are often the most optimal solution for a lot of applications. They can be used as a booster for other main horizontal pumps, especially when MPSH available in the plant is low and no sufficient pressure is present. There are various types of vertical pumps with standard or special options with both advantages or disadvantages, but always customized to meet all the customer technical specification. For sure, it's important to work with pump vendors who have a comprehensive range of pumps and want only steer proposal based on a narrow portfolio. Trillium offers not only a wide range of vertical pumps from 1 cubic meter per hour to more than 70,000 cubic meter per hour, but also has a technical experience covering a wide range of vertical suspender pumps applications, extensive service and troubleshooting support both for Trillium or 30-part pumps, and has a full refurbishment and quick ship parts availability. So that's all. Thank you for your attention, and we can switch to the question and answer session.
All right, thanks, Steve and Matteo, and thanks to the audience for asking some questions. So we'll kind of dive right in. The first one, actually, I'm going to kind of sort of merge two together. The one question was, what is a normal or good efficiency for vertical pump? And a sort of a similar question was what efficiencies we could expect with enamel lining and extrude hone impellers. Who wants to take that one?
Yeah, sure, Simon. I can field that one.
Go.
Yeah, so for vertical pumps, you know, you would consider, you know, kind of a good efficiency range anywhere from, you know, probably the high 70s to the high 80s, depending on the pump. And, you know, the physical size of the pump is a big factor, with efficiencies improving as you scale up the size of a given hydraulic. Yes, you can, you know, apply different, you know, smooth coatings, such as fusion bonded epoxy, or different surface treatments such as polishing or extrude honing. And from our experience, you know, you can gain anywhere from 1 to 3% typically with the addition of some of these features.
Yeah, thanks, Steve. Just to note, I mean, the theoretical upper efficiency for any centrifugal pump is around 91-ish%. Sometimes you can get a little bit beyond that, but that's basically where physics puts you, even, you know, regardless of the size of the pump. All right, next question, which is kind of like a follow-on here, I think. The question is asking about duty cycle as it affects the design and the efficiency of vertical pumps. You guys talked about earlier, the trade-off between efficiency and first cost. They're asking if there's an equation that kind of sort of helps satisfy or decide that trade-off, I guess. Does anybody want to take that one?
Well, yeah, I could try to address that one. Yeah, there's not an equation I'm aware of that I could cite off the top of my head. I think, you know, it could probably be worked out, you know, if you know what the duty cycle is, and say you're comparing two pumps and you know their efficiencies, you know, I would think it could all be worked out in a spreadsheet. Just calculate the comparison of the energy consumption, and you know.
I mean, a lot of it comes down to what is your cost of energy, and how often are you going to run the pump, as Steve mentioned earlier. So there isn't one size fits all. It's generally, there's certainly not an industry standard equation at this point in time, which I think is what the questioner was looking for. There's certainly, I know of certain end users who are very conscious of energy cost, who have an equation that they will evaluate. But unfortunately, there isn't one single equation, to Steve's point. Okay, next question. MPSHA calculation for VS pumps. What's the datum reference the questioner is asking, or they're asking if it is the impeller eye, and the answer is yes, it is the impeller eye. That's the short answer. Next question. See where we're at. Sorry. Okay. the questioner is asking about using VFDs for flow control. So essentially, if I understand the questioner's question, in that scenario, there is no discharge control valve. You're just varying the speed of the pump in order to control the amount of flow that the pump is delivering. Does anybody want to kind of talk to that?
Yes.
Okay.
Yeah. For sure, VFD is a good solution to give flexibility to the pump in operation, and maybe you can achieve this kind of control using only a VFD, but I think that a control valve in a discharge pipe can be useful for sure for a lot of applications.
Sure. I'd kind of note it also very much depends on the system characteristic that you have.
Yeah.
So,
and how many pumps are working?
Yeah,
running
I mean,
together.
if you've got a system characteristic that is mostly static head, so the friction head is low, but the static head is high, so it's essentially a very flat system curve. Using a VFD for control probably isn't your best idea. It's not going to give you very good control. Okay, what's next? So there's a question about CFD modeling, and how is the question that they asked is, how is CFD modeling in compliance with Hydraulic Institute standard 9.8.8? If it's okay, guys, I'll take this one. So
By all means.
yeah, so Hydraulic Institute 9.8.8, the latest version of that is dated at 2018, which is, by my reckoning, 6 years ago, and it was probably put together 1 or 2 years prior to that. So 6 to 8 years is a lifetime in CFD analysis in terms of the state of the art. Now, what they say in that standard is currently, as they wrote it back in 2018 or released it in 2018, they do not allow CFD to be CFD analysis to be in compliance with that standard. So that is true. However, as I said, 6 years have passed. CFD has got massively better since then, and whilst that they were reflecting what the current state of the art was back then, that we would submit is no longer the case. And at the end of the day, what matters is the correct prediction of the performance of the pump, regardless of whether you use models or CFD. And that's ultimately what is being delivered. CFD is one method of delivering that, as Matteo talked about. It's not the only one, but it's certainly in a lot of instances is faster and more cost effective. And then I think we have time maybe for one more question before people kick me out. The questioner asks is, are there any other means of fabrication that can be implemented to increase pump efficiency? You mentioned enamel linings, honed impellers, and tapered column transitions. Are there any others that could be specified? Who wants to take that one?
Yeah.
Okay.
Oh,
would you like to speak? It's not a problem.
Yeah, I was going to say there are probably a couple that less common ones that I haven't mentioned. With regard to discharge head design, you can go with a fully radiused elbow, which is yet a step up further from the mitered elbow we presented. As far as anything else beyond surface treatments and coatings, I think on rare occasions, maybe modifications of the impeller can sometimes, help there. But that's something that's done extremely rarely in my experience.
For low specific speed application, for example, you can use narrow gaps in the wearings, for example.
Yeah, I was going to say wearing clearances is another one. Use of non-metallics. We use clearances.
Or non-metallic. Yeah.
The amount that you get is very dependent on the specific speed of the pump. Those are probably the main ones. And then we got one final one that snuck in at the end here. Why do some customers not accept vertical pumps higher than 1500 RPM? Does anybody want to take that one, or you want me to kind of hold forth on that?
Yes, let's get your thoughts on that one.
So it's actually normally a 4-pole limitation, so 1800 RPM or lower is what they do. And you see a number of end users have applied this. You know, for example, Saudi Aramco do so, and I think as best I can characterize it, just reflects their experience that that running at higher speeds, your wear and your problems tend to be multiplied more, and they've found that the maintenance overhead and the troubleshooting of such pumps becomes more problematic, and that's why they've decided to draw the line there. That's not to say there aren't many instances of 2-pole pumps running effectively. It's just that they do require more care and attention, and the maintenance overhead is likely to be higher, you know, based on field feedback. So I think we're going to stop there because we're like well over time, and I'm going to get yelled at pretty soon by our moderator. So we'll kind of close it there. Thank you everybody for your attendance. Thank you, Steve Matteo, for an excellent presentation. And as I said, it will be on the Trillium Flow Technologies YouTube channel in a few days. Thank you very much.
Thank you.
Thank you. Bye.